Yes, I know there's some
Came in since I walked out. All right. I believe there are some people who have questions. Any questions?
Can you go over number 8, please?
I will need to see what number 8 is. The Mars problem. All right, so we drop it out, so I give you the weight and I give you the height. Then I tell you the distance. It stops. Let me make some notes and I'll hand it back to you. Planet, weight. And then I have, let's see, it's positive. And then for time, speed. Average. This is falling. And then all right. I'll use different numbers. So let's make this Venus. With a weight of 20 newtons as measured on Venus. It's going to fall 50 meters. And then it hits pavement still. And it stops in, we'll just say 10 centimeters. I think all those numbers are different than what are on there. All right, so why did I tell you the planet? What does that affect? Okay. If we're dealing with something falling more specifically, not just the pull.
The acceleration due to gravity.
There we go. And the acceleration due to gravity on Venus, anyone happen to know? I'm going to make up a number that's based off of some memory. I think it's 8.7 meters per second squared. That could be off. If it turns out that Venus is not, that it does not have that acceleration due to gravity, then it's on some mystery planet that just happens to have the same name as the second planet of our solar system. All right, so we have an object that is falling at that acceleration. I said make down positive, so we will keep that. And I know it's going to go 50 meters. So the first question I asked was, how much time does it take to fall? Well, there's a formula that since this object is dropped, what does dropped imply? Okay, dropped, okay, that's part of it. So we're dealing with some acceleration due to gravity, assuming that it's not falling too far. I just want to point out, as people come in late and they come within the camera's screen, you all have an alibi for this time. So congratulations. If anyone needs an alibi, just sort of poke your head right there in front of it at some point. All right, so as this object is falling, there's one other implication of the fact of drop.
From the time it leaves the hand.
That would be the question. All right, let's do it this way. Is that drop?
No.
So what's the difference between dropped and throwing it?
Force.
There's a weight behind it.
There's a weight behind it whether I throw it or drop it.
The force you use.
It's mine, did it put the kids down?
All right.
Starting point.
Apparently mind reading skills are off again this morning. The initial speed is 0. If it's dropped, it's implied in the word drop that the initial speed is 0. It's starting from rest. So dropped, starting from rest. And that is an A there, despite the way it might look. So Hewitt has a formula which deals with distance and time for an object that starts at rest. And it's the fact that the distance that it goes is going to be equal to 1/2 gt squared. Somewhere near the end of chapter 3, I believe. Yeah, page 48. I know the distance it's going to fall, 50, given those numbers. It's equal to 1/2 times 8.7 times t squared. So it's a matter of solving for t. Again, have had a wide variety of math abilities in this class over the years. So if you're looking at that and sort of freaking out, let's just take it step by step. First off, let's just multiply 1/2 times 8.7. There are other ways of doing it. This is just one way. And that would be 4.35. T squared hasn't gone away. We're sort of peeling away the layers of the onion. We're trying to get to that hard caramel center of the math candy that this is. We're trying to get to t squared, so we have to get rid of everything else. So let's get rid of the 4.35 first. That which is farthest away in this sense. And since there's multiplication going on there, we get rid of it by dividing. On the right-hand side, that cancels out. So I'm left with t squared, whatever 50 divided by 4.35 is.
Quick question. That 1/2 from the very top, where did you get that from?
Where'd the 1/2 come from?
Yeah.
Well, Hewitt presents it, the 1/2 in there, but it comes from that the distance an object, or the displacement of an object, is equal to the average velocity times time. So if something is starting at rest, the initial velocity is 0, and its final velocity is not 0, because it's falling. Well, if it's in free fall, that is, the acceleration therefore is 8.7 meters per second squared, or meters per second every second. So if it starts out at 0, if that's my initial velocity, that's in seconds, and that's in meters per second. After 1 second, it's going 8.7 meters per second. After 2 seconds, it's going whatever twice that is, so that's 17.4 meters per second. So the velocity changes by 8.7 meters per second every second. So whatever the time is, all I have to do is multiply that. So at some time, my velocity is just time times this. So 8.7 times however much time has passed. Or in general, GT. My average velocity is just the average of the first and the last part. Well, I start at 0, I end up at whatever GT is. So my average velocity is 1/2 0 plus GT. We get a 1/2 GT times T, or T squared. That's where it comes from. It has two major assumptions. This formula has two major assumptions. One, it starts at rest, and two, acceleration is close enough to constant. And we are assuming over 50 meters on a planet, acceleration is not going to change significantly. Matter of fact, if you're at the edge of what's considered space, 100 kilometers up, the acceleration of gravity at 100 kilometers up, so 100,000 meters up, is 9.2 meters per second squared. Not significantly different than what it is here on the surface. So anyway, what is t squared? What is, somebody's done this side.
11.49.
So now we have to get, again, we're trying to get t by itself, so we have to get rid of the square. We do that by square rooting. So whatever the square root of 11.49 is.
3.39.
One more time.
3.39 seconds.
Thank you. So that's the amount of time it takes for this thing to fall. How fast is it going when it, just before it hits the pavement? After it's fallen to 50 meters, how fast is it going? Well, just based on answering Lewis's question, to find how fast it's going, I just multiplied the acceleration times time, which is also one of the Hewitt formulas that he presents in the free fall section on page 46. Or final velocity equals acceleration times time if the initial velocity is 0 meters per second. Technically, it should be a 0 vector. So we do 8.7 times 3.39. So we get something spectacular. That's 0.4 there, so somewhere around 26 or so. Someone's about to tell me. Finish it off.
Per second.
There we go. As a group, we got it. So that's how fast it's going just before it hits. What's the average velocity? It starts at 0, it ends up at this. How would you find the average?
You take the final and initial, subtract them and divide by, or no, by 2, sorry.
Close.
Okay.
And this is why you should show your work. You had one word off.
Oh, okay, add them.
Yes.
Sorry, add them.
Yeah.
I keep doing that every time I say that.
If you subtract and divide by time, you get
Right.
acceleration. Hopefully you'll get 8.7.
Yeah.
But the average, add them and divide by 2,
Yeah.
as was talked about over here. All right, so we had started at 0 plus 29.49 divided by 2. And that's going to be something just shy of 15, so somewhere around 14.75. How about 745? Is that? And I could easily have just made a Carol's error.
So
Confirmation.
you're doing starting plus final
Yep.
divided by 2.
This works as long as acceleration is constant.
Okay.
And we're going to run with this. And I've got a nod. Okay. All right. So that takes care of the following part of that particular problem. Questions up to here? Okay, Amina?
So the 2 is part of a formula, right?
This 2 right here, just when you average numbers, you add up whatever you're averaging and then divide by how many numbers you have.
Oh, okay.
Yeah, this is just the straight up averaging 2.
Okay. So if it was like 5 numbers, then it would be 5?
Yes, absolutely. And you can do it that way, it's just a lot longer to do it that way. Yes,
So
Brittany?
I saw a formula for speed equals distance divided by time, so you could not just take, okay, so it's asking something different, that's why you didn't do that. Just before it touches the pavement, that would be like the average speed if we did it like that, right?
Yeah, in this particular problem, you could have done 50 divided by 3.39. And you should have gotten the same thing.
Oh, okay, I did that, and I was just wondering if that was wrong, so.
No.
Okay,
Matter of fact, that formula right there works even if acceleration is not constant.
oh, really, okay.
But as usual, which one's simpler is the way your mind's working at that moment. My mind was on the other one at that moment.
That, the other one's simpler.
Other questions right now? Lydia?
For the, average velocity, I got 14.75. Do you want all three or just two?
Two is fine.
Okay.
Yeah, hopefully if I design any test correctly, the difference between what you said and what I said would not make any significant difference in the end. All right. So now the stopping. We know how fast it's going right before it hits the pavement, so that's how fast it's going when it first hits the pavement. That first moment of contact. So we have now changed, let's see, I'll need, let's not need that anymore. So now stopping. It's going 0.1 meters. And I do recommend, if I give it to you in centimeters, I do recommend putting it in terms of meters since that was in meters. Unless you want to track units. It's going 29.49 meters per second. How fast is it going at the very end? I hope so. Because I think in the problem I do state that it stops, right?
Mm-hmm.
Yep. So 0 meters per second. So one of the questions, I think the question number 4 or D, whichever way I labeled it, what's the average velocity as it stops? If we assume acceleration is constant.
Same as,
Yep, it should be the same. The only difference is if you're doing this in order of initial and final, is that this flip, but it's still the same two numbers I'm averaging. So my average, if I ask for average velocity, I said down is positive, so it would just be a positive number of 14.745 meters per second. If I said average speed, well, it's still the same answer. Now I'm asking for the time it takes to stop. Yes?
Are those just like random numbers or those are the actual?
Same problem, different numbers.
Oh,
I put this one on Venus instead of on Mars, I think it was.
yeah.
And so that number will be different. I gave it a different weight and a different distance it's falling, a different distance it takes to stop.
Okay.
I think all the numbers are different, but the process is the same.
Okay.
Other questions right now? Amina?
So what number would it be for gravity to Mars?
2.7, if you just go on the internet, acceleration to gravity, Mars, it'll pop that up. Or if you look at old tests, it might be on there. If I guess I didn't give it to you. Anybody happen to know acceleration due to gravity on Mars?
3.7.
What's it?
3.7.
3.7 meters per second squared, I assume.
So reading the other
Pardon?
like, it's, well, They're not wrong, it's just that it's at 3.721, so we didn't need to choose that.
Yeah. I mean, if you did it, there's nothing wrong with that.
Okay.
I mean, as, like on Earth, you could go more decimal places, but it really starts to vary more depending on where you are. So 3.7 is fine, meters per second squared.
Thank you.
Other questions right now? All right, the time it takes to fall. I know the average velocity. I know the displacement. How would I find average velocity? Or if it's speed, I know the distance it's falling, and I know what the speed, average speed is. I know the distance it falls. How do I find time? This goes back to what Brittany was asking.
Distance times speed?
Distance times speed?
Yeah.
Let's see what that would do in terms of units. So let's get rid of some stuff. So if I did distance times speed, this would be in meters. This would be in meters per second. If I multiplied those, what would I get for my final units?
In square root of
Not a traditional unit of time. Matter of fact, we'll just go ahead and say it's not a unit of time. So distance times speed is not going to do it.
divided by?
So delta x divided by v? Is that what I?
I don't know, yeah, that's what I said, I don't think it's right.
Well, let's see. That if we look at just the units here, we get meters over meters per second. So I've got this fraction here with a fraction in the denominator. Remember, a fraction is just division. That's all a fraction is. So that becomes meters divided by meters per second. And when you divide by a